Welcome to the Deep Dive. Today we're really locking onto the world of advanced structural materials, specifically how engineers are trying to figure out the actual strength of concrete that can, well, essentially pour itself.
That's right.
We're diving into a new procedure that seems to correct a, frankly, huge flaw in how we measure fracture resistance. And the results, they're pretty surprising.
Yeah, they really are. Our sources today introduce us to something called steel fiber reinforced self-compacting concrete, FRSCC for short. And this novel experimental method called the matrix crack, or MC method, because, well, for decades it looks like the standard tests have made us severely underestimate how tough this stuff really is, especially against sliding cracks.
Right. So our mission for you today is pretty straightforward. We want you to get what FRSCC is, why its resistance to shear cracking, that's mode 2 fracture toughness to engineers, is so vital in the real world. And crucially, how this new MC approach is showing strength values that are, in some cases, almost double what we previously thought.
Exactly. And to really get why this is such a big deal, we probably need to start with the basics. Self-compacting concrete, SCC.
Okay.
This is a high-performance concrete, came out of Japan initially, designed to solve a major headache in construction.
Which is getting concrete into really tricky spots, right? Like narrow forms or areas packed with rebar.
Yeah.
Without leaving air pockets or weak zones.
Precisely. Normally you need to vibrate concrete like crazy to get it to settle properly. But SCC, it's designed to flow almost like a thick liquid, a heavy syrup maybe.
So it just fills everything up by itself.
Under its own weight, yeah. It speeds up construction a lot, and importantly, it helps avoid those flaws of, porous sections, bad bonding around the steel that sometimes happen even with vibration in really congested areas.
Okay, that makes sense. But concrete, even this fancy SCC, it's still fundamentally brittle, isn't it? It cracks rather than stretches.
That's its main weakness, yeah. Brittle failure.
So how do you toughen it up?
That's where the F comes in the fibers. That's the upgrade that turns SCC into FRSCC. The study we're looking at used specific steel fibers hooked ends, about 50 millimeters long, and adding these just transforms the material. You get much better toughness, much better performance when it's bent or pulled, and way better energy absorption when it's under stress.
That sounds fantastic. But I'm guessing throwing a bunch of steel bits into a superfluid concrete mix isn't entirely straightforward. There must be downsides.
Oh, absolutely. You're right. The sources are clear on this. While the hardened properties improve, you've got to be really careful with the mix design. Too many fibers, or if they don't disperse well, you can mess up those crucial fresh state properties.
Meaning how it flows.
Exactly. Its ability to flow, get around obstacles without separating, the fibers clumping together or sinking. It's a delicate balance.
Okay, got it. Let's shift to the core engineering problem here. Fracture modes. Mode 1's the common one, the crack opening up under tension. We study that a lot. But this research is all about mode 2. Why is that sliding or shearing motion so important, maybe even more critical sometimes?
Well, mode 2 failure, the sliding or shear mode, it's incredibly important because it reflects how things often fail in real structures.
Yeah.
Think about layers in a beam trying to slide past each other, or cracks at joints, or deep shear failure inside a concrete element.
Right, those sound serious.
They are. They can be sudden catastrophic failures. So accurately measuring the resistance to that kind of failure is absolutely critical for safe design.
And for FRSCC, that measurement has been problematic. You mentioned the traditional test uses a double-notched cube specimen, the DNC, but prepared with a through-thickness crack, TTC. What's wrong with TTC?
Okay, this is really the heart of the matter. With FRSCC, almost all the extra toughness, the resistance to the crack growing, comes from the fiber bridging effect.
Right, bridging.
Yeah, as the crack tries to open or slide, those steel fibers span across the gap. They literally hold the two sides together like tiny ropes absorbing energy.
Okay, so the fibers crossing the crack are the key.
They are the key. But the traditional TTC method, they prepare the starter crack by cutting it with a saw. And when you saw through it, you cut all the fibers right at the crack plane.
So no bridging.
None. By definition, the TTC method ensures that the most important toughening mechanism is completely absent.
You're basically testing the material without the very thing that gives it its enhanced strength in that situation. That seems fundamentally wrong.
It is. It leads to a massive underestimation. It's like, testing a climbing rope strength after you've already cut most of the strands. The result is meaningless for its real-world use.
Okay, so that sets the stage perfectly for the innovation here. This matrix crack, or MC, procedure, proposed by Salem and co-workers. Right.
That's the one. And this study applies it to Mode 2 testing for, it seems, the first time. It's designed specifically to overcome that fatal flaw of the TTC method. The MC technique lets you create a pre-crack, but keeps the fiber bridging intact across that crack.
How did they actually run the test? What was the setup?
So they used standard DNC specimens, 150 millimeter cubes. They varied a couple of things. The notch depth relative to the width-the-yaw ratio testing, 0.30, 0.4, and 0.5. And they also varied the amount of fibers, the volume fraction, VF%, using 1.0% and 1.5%.
Okay. And calculating the toughness, the KIIC value.
They used a standard formula, Watkins's formula, which is valid for those notch depths. It just uses the peak load measured in the test and the specimen dimensions.
But the really clever part, as you mentioned, wasn't just comparing old TTC to new MC. They used 4 different types of specimens to really isolate what was going on.
Exactly. Good experimental design. First, the baseline, plain SCC, no fibers at all, just the basic concrete strength.
Makes sense. Then the old flawed standard.
That was Series 2, TTC. Through thickness crack. Fibers are mixed throughout the concrete block, but because the crack is saw-cut, absolutely 0 fibers cross that initial crack plane. This gives you that unrealistically low toughness value.
Okay, they're the really interesting ones.
Series 3 was, I thought, particularly smart. They called it MCC, matrix crack-crack. Here, they only put fibers right along the surfaces of the intended crack. The rest of the cube was plain SCC.
So that isolates just the bridging effect.
Precisely. It tells you how much strength comes only from fibers spanning the gap without any contribution from fibers elsewhere in the material.
And finally, the realistic one.
Series 4, MEC, the matrix crack specimen. Fibers uniformly distributed everywhere, including across that carefully created crack surface. This represents the actual material in a structure.
You have to talk about how they made those MC cracks. You mentioned it preserves the bridging. How?
It's pretty ingenious, actually. Instead of cutting, they inserted thin foam panels, just 2 millimeters thick, into the mold right where they wanted the crack to be.
Foam panels. Inside the concrete mold.
Yep. And here's the clever bit. They actually glued some of the steel fibers directly onto these foam panels before pouring the concrete.
Okay.
Then, after the concrete hardened, they removed the foam.
How?
They dissolved it using gasoline.
Wait, seriously? They use gasoline to dissolve foam inside a block of concrete to leave behind a crack with intact fibers.
That's exactly what they did. It leaves behind a perfect crack interface, but the fibers that were attached to the foam are now bridging that gap, just like they would in a real crack forming in a structure.
That is brilliant, and probably requires good ventilation.
Yeah.
Okay, so the big reveal. What did the results show? Did leaving the fibers intact make a difference?
A massive difference. The results were crystal clear. The MC specimens, the realistic ones, consistently gave the highest KIIC values, the highest shear toughness. They showed the most effective enhancement by the fibers. And, as you'd expect, the plain SCC without any fibers had the lowest toughness.
Let's nail down that underestimation factor.
Yeah.
Comparing the realistic MC results to the old TTC method, how much stronger was the material really?
It was dramatic. For the specimens with 1.0% fiber content, comparing MC to TTC, at the shallowest notch depth ratio, A equals 0.3, the KIIC from the MC method was 1.95 times higher than the KIIC from the TTC method.
Wow, almost double the shear strength. That implies engineers using the old data might have been designing structures thinking this material was only half as resistant to sliding failure as it actually is.
That's the implication, yes. It's a huge correction. And even at the deepest notch, AI equals 0.5, which tends towards a pure shear failure. Even there, the MC toughness was still 1.31 times higher than TTC. So across the range they tested, the traditional method significantly underestimates the real strength.
It's misleading.
What about that other comparison? The MCC fibers only at the crack versus the TTC fibers everywhere but the crack. That comparison really hammered home where the toughness comes from. It showed that having fibers right there, bridging the crack surfaces, MCC, is far more important for shear resistance than just having fibers distributed in the material ahead of the crack tip. TTC.
So placement is key.
Location, 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 you could say. It's the bridging that does the heavy lifting, and this ties into how the specimens failed too.
Right, the failure modes, what did they look like?
The plain SCC, the baseline concrete, it failed in a very brittle way. Clean, smooth, shear fracture surface, sudden drop in load carrying capacity right after the peak. Snap.
The classic brittle failure.
Exactly. But the MC and the MCC specimens, completely different story. You could actually see evidence of fiber pullout on the fracture surfaces. Instead of a clean break, the fibers were pulled out of the concrete matrix as the crack tried to slide. This pullout process absorbs a tremendous amount of energy.
Ah, so it's not just preventing the crack, it's making the failure itself much less dangerous.
Precisely. It provides ductility. The load doesn't just drop off a cliff after the peak. There's a gradual decrease. It hangs on. That's the definition of toughness, and it's what you want in a structure.
Okay, one more key variable, fiber content. They tested 1.0% and 1.5% fibers. Did adding 50% more fibers give a 50% strength boost?
Interestingly, no, not at all. That was another really key finding. Increasing the fiber volume fraction from 1.0% to 1.5% only gave a marginal increase in the shear toughness for the realistic MC specimens. We're talking around 5%.
Wow. So a 50% increase in fibers, which presumably adds cost and complexity to the mix, only yielded a tiny, maybe 5% increase in shear performance? That sounds like diminishing returns kicking in hard.
It really does. It strongly suggests there might be a saturation point. Once you get to about 1.0% fiber content, maybe the bridging mechanism is already working near its peak efficiency for this setup. Adding more fibers beyond that, perhaps they don't align as effectively across the crack, or maybe they even start to clump slightly, hindering rather than helping. It certainly indicates that just adding more fibers isn't necessarily the answer.
Okay, let's pull this all together. The big takeaway for engineers designing with this material.
It seems pretty definitive. The study makes a strong case that this MC-DNC specimen, the matrix crack approach, is the proper way, maybe the only reliable way currently, to measure the true Mode 2 fracture toughness of FRSCC.
Because it actually includes the fiber bridging effect.
Right, whereas the traditional TTC method, by saw cutting the crack, intentionally removes that critical mechanism and gives you a dangerously low estimate of the material's strength. It's just not suitable.
So this new method gives engineers more trustworthy numbers for shear resistance.
Yes, which allows for safer, potentially more efficient designs, especially when you're dealing with failure modes like shear slip, which happen all the time in real concrete structures. Engineers can now have more confidence in the material properties they're using.
But like all good research, this study also points towards what we don't know yet, right? The limitations and next steps.
Absolutely. Two big ones stood out in the sources. First, this was all done using one size a cube, 150 millimeters. We really need follow-up work to look at the size effect.
Meaning, does the measured toughness stay the same if you test a much bigger block of concrete?
Exactly. For a material property to be truly useful in design, it needs to be independent of the specimen size, at least above a certain threshold. That needs verification for KIIC measured this way.
Okay. And the second limitation?
The second is about the loading itself. This study focused purely on Mode 2, pure shear, but in reality, cracks in structures rarely experience just pure shear or pure tension. It's usually a mix.
Mixed mode loading, like combined tension and shear.
Right. So the next logical step is to apply this MC methodology to investigate FRSCC behavior under those more realistic mixed mode conditions, Mode 3. That would give us an even more complete picture for designers.
Okay, that makes perfect sense. So as we wrap up, here's a final thought for you, our listener, to mull over. This research clearly showed that fibers right at the crack interface, bridging the gap, like in the MCC tests, were way more effective than just having fibers scattered in the concrete ahead of the crack, like in the TTC tests.
Yeah, the location was critical.
So if the real bottleneck isn't just the amount of fiber, but getting it precisely where it needs to be, perfectly oriented to resist that shear, what if future construction techniques could actually place or orient fibers deliberately? Imagine using, say, advanced formwork, maybe 3D printed molds, or even something like magnetic fields during casting. Could we engineer the fiber alignment specifically at points where we expect high shear stress? Could that unlock even more performance from FRSCC beyond just random distribution? Something to think about.